So today we're going to introduce normality assumption to the model. Then we talk about hypothesis testing. Okay, so that's basically the objective for today. But before I get started, I want you to go through some of the nice property of multinomial distribution. So this handout is posted in Canvas. Okay, so if you're interested, you can download and take a look. And I believe probably at the end of the text, I think one of the appendix also discuss some of the properties here, okay, but probably not as comprehensive as this here. You don't have to need, you don't need to know all of this, but I just want to point out a few important things regarding normal distribution, because multinomial distribution. Okay. So this is the setup. Suppose this is a random vector x. Okay. So we have p observations, and each of these is a random variables. Okay. So this is the mean, and this is general setup, mean and variance, right? So we have the diagonal term or the variance of each random variable, or off diagonal term will be the covariance between any two random variables included in this random vector here. Okay. So here typically we can written as this way. So the variance covariance matrix, we have a different variance corresponding to different random variables. This also row is a correlation coefficient. Okay. Should be 70 between -1 and 1. That's used some basic statistics. Okay. So this will be variance covariance. This will be the variance of each random variable. Then this would be called a mean vector. This is called a variance covariance matrix. I've already seen. I already look at the distribution. Look at the regression error when we have n observations. So typically we look at the error term. We will have n by n matrix, right? So the n error terms, and it will be n variance covariance matrix. Okay. So typically for this variance covariance matrix, it will be symmetric, as you can see at because covariance of x1 and x2 is the same as the covariance of x2 and x1. So that's why they are symmetric automatically. Okay, it's a symmetric, and it also should be positive semi-definite. Okay, it's kind of like related to the scalars, basically meaning like it cannot be negative. And a little bit more strict thing that the positive semi-definite is basically for any non-zero vector alpha. So that's what I mean. If this is just for knowledge, okay. So if a matrix, let's say if a matrix A is positive semi-definite, if and only if for any, let's say alpha, a vector which is not equal to 0, unless it's a 0 vector, okay. So we will have alpha prime alpha positive semi-definite, okay. So larger than or equal to 0. So this will become basically. This is basically scalar. Alpha, remember this is a vector, this is a matrix, okay? So this R prime A times A will be 1 by 1 scalar. So after you apply this one, this will be a scalar. Okay, so it will be number. So this number cannot be negative. So that's the meaning. So only way for this to equal to 0 is that you choose a 0 vector. That's basically what it means, okay? So this is kind of like a quadratic form. If you think about it, it's like a quadratic form of this positive semi-definite matrix. And if a positive definite, then basically this product of the alpha prime A prime R can be only be positive. Okay, so this is just for your knowledge. So this is a definition. In the matrix, this is how we define a matrix, a positive definite or positive semi-definite. You just need to know that basically the nice thing about this semi-definite matrix is that basically this is widely used in matrix in a lot of derivation, but for quite relevant to our discussion here that if a matrix is positive semi-definite, then can always find a matrix such that this matrix equal to D prime B. What does that mean? That means kind of like we can always think about just like in a scalar case, you can always take a square root. Okay, so it's kind of like the analogy to think about matrix versus scalar. Okay, so in the real, in scalar cases, we know for any real numbers, right, any positive real numbers, we can take square root. For example, if there are 2, we can only calculate square root 2. What's the square root 2? It's defined, right? But for negative number, we don't have square root. The only way we introduce the complex number, then we can take square root of negative number. That makes sense? So in the space of real numbers, negative, what is the square root of negative minus 9? It's not defined. Okay? So that's kind of like the idea. Because like in the matrix form, the basic think about if this matrix, remember this matrix is like a kind of like consider it's cannot be, this one cannot be negative to scalar, so it's kind of similar to scalar. It's like a positive non-negative number. So we can always take square root. So it's a square root, so b is kind of square root. Okay, so sometimes we can say that b is like in slope to right, is like in this case, if a is definitely matrix, so we can always find a, we can always take this one. So this will be well defined. So we can define this b as this. Okay, is that okay? So that's what basically what it kind of means. And that's a bit abstract, but you know, if you link to the scalar cases, that's probably help you understand. So think about this as a non-negative number, then we can take a square root, so this will exist. Like for example, 9, then take a square root equal to 3. But this is kind of like an analogy for in the matrix. So if our matrix is positive sign definite, then we can calculate the square roots. So the square root in the matrix they represent this b times b transpose will be equal to this. Okay. So that's basically later on I'm going to use this. Okay. So that's it. Okay. So let's look at a few. This is just a general discussion for the matrix. Then here we're talking about the multivariate non-distributed. Okay. There are quite a few nice properties. Okay. So I won't go through every property. First of all, you can think about it. If this A prime is a vector in real space, so this is like A prime, you can think about the linear combination. Okay? If X is a multivariate, then if a linear combination of this still it's a multivariate normal. In this case, the mean will be equal to A prime times the mean of the matrix, then the variance will be this is the variance covariance matrix of X, then with A prime. It's kind of like something like 8 squared. Okay, like this. Okay, so basically we say that okay, a linear combination of normals still be normal. Let's put this way. And then this again, it's a pretty easy. I put a scalar here, and still it's a normal. Okay, so it's kind of general. It's an extension of A, so with a constant term still normal. Okay, and then see here that if these two are independent, normal, then combine them will still be normal and will be bivariate if you think about this. Okay, so if x1, x2 independent normal, then combine them, then become a bivariate normal with covariance being equal to 0. Okay, then this is basically saying that this sum. Okay, sum of the normals still be normal. Okay, and it's also not easy to see. It's kind of interesting that the mean will be the sum of the mean of the two normal, and the variance current is like a sum. Obviously these are independent, so therefore the offline still could be 0. Okay. Then margin distribution is also normal. If a multivariate normal, then margin distribution is also normal. Then this will be probably is a nice thing for this multivariate normal. So in this case, we see that the uncorrelation, this is basically the correlation is equal to 0, right? So this correlation will be the same as independence. So in class 1, when we reviewed the basic property statistics, independence is much stronger than uncorrelation. Right? Independence implies 0 correlation, but not the other way. So 0 correlation is much weaker than independence. Independence put a stronger because independence can mean that these two random variables are uncorrelated in all dimensions, whether it's a linear or a nonlinear situation. So it's stronger. However, in the case of a multivariate normal distribution, actually the correlation and independence, also zero correlation and independence are equivalent to each other. So that makes the analysis of some multivariate normal distribution much more convenient, much easier, okay? So this one I want to say, then actually this one can be extended to this. In other words, if this is a multinormal distribution, okay, and we actually can apply this again to a linear combination of x, then another linear combination of x, so we're using B and C, these two transformations, right? So these two combinations will be independent if and only if this term is equal to 0, so it's kind of similar, right? So we can think about F, G is extension of F, in the sense that if in the case of B is identity matrix and C is identity matrix, that basically is a theorem F. Does that make sense? So if both B and C are identity matrix, then we get theorem F. Okay, so that's why G is an extension of F. It's more general. So as long as this product is equal to 0, then these two will be regarded as independent, and vice versa. Now another, very important property for multinormal distribution, which is theorem H, okay? So essentially here, if x1, x2 followed by very normal distribution, then we can calculate, look at a condition distribution. Condition distribution x1, condition x2 have the mean of this and variance of this. So what does that mean? This, it's a little bit, now this may seem a little bit more abstract, because now x1, x2 are two vectors. So let's think about x1, x2 just univariate random variables. So now it's a simplified way to look at this x1, x2, okay? So that's x1 random variable 1. So H essentially, simplified case is that for Barbara normal. So if let's say, for example, x1, x2, by this one, okay, so just to help on that H, okay? H is a bit, because H is as in terms of matrix, okay, vectors. So let's say x1, x2. x1 is one scalar, okay, x2 is another scalar. So this is basically following by very normal. So essentially, they have mu1, mu2. So they are, and this is a reference matrix, okay? So here there's a scalar random variable, there's another standard random variable, so now this is a very normal distribution. So we calculate all this matrix. So essentially what does that mean? That means that x1, if look at the condition distribution of x1 given x2, it's a still normal. Okay, we can see that it's a still normal distribution. Okay, then the mean will be equal to, so let me use this. Okay, this is the, so it's probably easy for me to write. So actually this is a, let's see like this. So probably it's an easy way to look at this one. So you can think about what's this. If you know a little bit of basic, this is kind of like this one. If you know a little bit this term, what's this? This is basically when you run regression of x1 to x2 and the beta coefficient. If you run this, suppose if you run this model like this x1 equals beta 0, for example, you run this regression. Beta 1 basically is. belonging to this system. Okay, so you can see the beta 1 is basically equal to the covariance between the two divided by the variance of x2. Okay? So remember, this is conditional expectation, this is conditional distribution. So essentially we can see that this is forecasted. If you think about the calculated mean of this x1, a lot of times you think about this is y. For example, y or given x. Okay? So basically round regression of this, we get this one. Then the mean is basically equal to unconditional mean, which is mu1, plus something else. This is, you think about this is the kind of information you can learn from regress of x1 capital x2, you did the coefficient here. So this is something additional. The mean. Okay, so this is kind of the information you learn about x1 given availability of x2. Okay, so this part. So this will improve your, forecast of the mean from the unconditional mean to something else. Is that clear here? So this is unconditional. So this mu1 is basically unconditional. So without relying any information, we know this is the mean. This is unconditional mean of x1. So if you think, okay, that this is what it is, okay. Now the even more nice way to look at this one. This is what? This is the conditional variance. So this is the variance of x1 given availability of about x2. So this is the unconditional variance. So here says the conditional variance will be smaller, right? Conditional variance will be smaller than the unconditional variance. The decreasing variance is basically captured by this time. Okay? And if you do a little bit more, this one you can see this is equal to okay? So rho is basically this rho is equal to rho correlation coefficient between the two. Okay, it's a very easy for you to see because sigma 1 squared is basically equal to rho square this one. Okay, and you can quickly derive this as basically like this. So in other words, the conditional variance of x1 given x2 is smaller than unconditional variance. Okay, and you can see that very intuitive. The more correlated between x1 and x2. In other words, the more information contained in x2 about x1, then the more accurate you're going to explain. Why? Why accurate? Because these rows are higher. Then extreme cases are perfectly correlated. Rho equal to 1. If rho equal to 1, rho squared is 1. 1 minus 1 is 0. So basically you learn everything about this x1. Okay, so it's pretty easy for you to see that the higher correlation, or in other words, the more information content in x2 about x1, then the better you're able to learn about x1. Conditional, you observe x2. Does that make sense? So that's a very useful. So if not here x1, x2, but if you think about it, like repeat this one. X1 is a y, x2 is some explaining variable for y. So now you can see that's pretty easy, right? So a lot of time, then y-inner regression, so that's pretty easy. So you see that the conditional variance of y, which you want to learn, will be much smaller if x contains all information about y, okay? So that's sort of, a simple way to look at it. Here, always a little bit more abstract because we look at the variable in the matrix thing, but basically that's what it is, okay? So the nice thing about the continued distribution of Barber normal distribution is still normal, and you can see that the conditional variance will be smaller than unconditional variance, and the mean basically will be captured by this additional information then. We're looking at x2. Okay. Then the remaining things, okay, so I don't want to spend too much time. It's basically, oh, actually, I also need to look at J. So here, J is also an important thing, okay, so here, keep this one, so the important Y, this is density function, okay, you need to get, get used to this kind of density function for whatever very normal. Why is important? Because if you want to do max likelihood estimate, okay, so if you want to do around MLE, then you need to write out the likelihood, right, Y given X. So a lot of time you can see that the likelihood will be based on this. And if you remember I think the first day of class, or maybe the second class, I derived some max likelihood estimate, essentially like this, okay? So this is this is called the determinant matrix. So here is determinant matrix, okay? So you need to calculate determinant. Otherwise, it's basically this is kind of like as a scalar term. So all the time you care about this. So J is important because when you do likelihood function, then this is the basis, benchmark to start with. And K, okay, K is also useful. So here you can think about this is kind of like, if another way to help to understand this is basically remember, this one is positive definite matrix, right? We know that variance converse matrix is positive definite. As a result, that can be from the square root. Okay? From square root. So what does that mean? So this means, roughly speaking, it's kind of like this. So it's kind of like we are looking at, if we are able to do this, okay, obviously this is a little bit sloppy way to do this, okay? So remember this, now here we're talking about this guy, okay, because we're going to matrix A here, okay? So, since this is a positive sum definite, and based on the previous discussion, we can find out always the square root of this matrix. Okay? So, obviously, take inverse still works, right? Because as positive it's invertible. So, essentially, this is this. So, the inverse base is like this. Think about this a bit. What is this? Okay? Or some other way, if you put this B here, is basically. You can write down this. Okay, so if we find this kind of square root, then B inverse is like this. Okay, so what's this? If you remember what this? This is kind of like a standardized. If a normal distribution with mean, remember, if a normal distribution with mean mu and a variance sigma, so x minus mu, then divided by square root of this is basically standardizing. That's the way we typically use as normal, right? So this, we know that this normal will be following 0, 1, mean 0 and variance being equal to 1, because standardizing. That make sense? So essentially, this seems kind of like a character of this. Sloppy way to look at the thing about this. To understand this. So this is what? This is just like a z squared. If you have a normal distribution with mean, mu, and sigma, then we standardize. So x minus mu divided by square root of sigma square. So that's basically standard normal. So for standard normal square, what is this? It's a chi-square distribution. Remember we did review this? Obviously this is in the matrix form. So we get a chi-square distribution. Okay? And so this will be chi-square distribution, okay, for this one. So here obviously, depending on the dimension of this x, so here's multiplied by x squared, p, okay? So degree of freedom p will depend on the dimension of x. Now, if obviously, it's much easier for you to see that when p is equal to 1. So in other words, x is a scalar random variable. It's a normal distribution, then clearly that's chi-square 1, because we're just looking at the z-square. Okay, then we can skip some of this I. Okay, the remaining I think you can leave for you. I don't need to go through everything here. Okay, just for your knowledge. So now regarding this, regarding this I would like to come a little bit more for this. So this chi, okay, so now from here, okay, so here since we know that for the scalar case, that p equal to 1 for the regarding this p, this is p equal to 1. So basically that means that is an x. This one, okay, what kind of this one? So this is a chi-square degree of 1. So that's an implication for I. Okay, so let me try to. That's what K. Okay, so what kind of K here? Okay, so for K, for theorem K, if P is equal to 1, that's pretty easy for you to see. Everything running is scalar. So we basically this is Z, right? This is the basic definition of Z. So now Z squared. Okay, so typically we define this Z squared so here. So one implication for this is basically we look at S, sample squared S. Okay? So if you construct sample variance of S, then here you can see that it will be equal to this n number of degree. Okay, so n times s squared divided by the sigma square will be equal to chi square of n minus 1. Okay. Then actually this will be the foundation to look at what's the F distribution. Again, I don't want to go through the proof for this, just to bring to your attention. So K is quite important, especially later on we talk about distribution. When we look at hypothesis testing. So this will be useful, okay? So that's pretty much the review I'd like to discuss. Again, I said if this is just for your knowledge, you really don't need to worry too much about anything. But if you are interested, you can take a look at this, and also probably want to look at the pennies or some related statistics book to look at this normal distribution. So now that said, okay, let me go to our lecture. Okay. So for this one, we know that so far we have discussed the so-called classical linear regression model, right? We have a few assumptions here. So we have basically 4 assumptions, okay? First of all, we know that can return this by just being y, x. Okay. So can return this. Actually, this implies that, okay, so first of all, implies EYX is equal to X beta, so it's a linear model, right? So we know that's a linear model. Then we also know that, so for model, let me write on this one, okay, this is the linear model we're talking about. So we have linearity, the opposite is linearity. So now implicitly we also know that strict exogeneity. So the exogeneity assumption for this, right? So I can raise this, basically these are the two things, in probably more better way to look at this one. Then we also know that spherical error, okay? Okay, and this, and then the matrix. And also we know that the x prime x full rank are invertible. So invertible and the full rank condition are basically equivalent to each other, okay? So that's basically what the assumption we have here, right? So basically we have four assumptions here. So we have a linear model, strict exogeneity, spherical error, plus full rank condition for x. So then we basically derive the Gauss-Markov theorem, which is saying, okay, so we know that the OS, okay, so this OS estimated, which is given like this, is a blue. Okay, that's basically Gauss-Markov theorem. So we have four assumptions so far. Then last couple we'll discuss a few other things regarding classical linear regression model. Now, this helps us understand the property of OS estimator, but still not sufficient for us to conduct so-called hypothesis testing. So for the hypothesis testing, we also need to know the distribution of the error term. Okay, so this will be the fifth assumption we can introduce to this model. So we impose the normality distribution assumption on this term, okay, on the error term. So if we also assume that this epsilon is a Fortian normal distribution, obviously here because epsilon is vector n vector, right, n time one vector. So obviously we're talking about the Bavarian norm. Okay, so if epsilon Fortian Bavarian norm distribution with this, okay, so if we, this will be four assumptions, okay. So now I have fifth assumption, so assumption number 5. This is a combined, this is basically this, writing this combined four assumptions here, 1, 2, 3, 4. Okay, this way, right on this one, so I didn't include anything. So you impose assumption 5, okay, so here, let me be specific, this n, because epsilon is n times 1 factor. So if you impose this normal distribution on this with fifth assumption, so given the model property we have discussed before, because this is a wide basically linear combination of epsilon, right? So as a result, we carry the y given x. So now with this assumption, plus this, so basically now we obtain the so-called classical normal linear regression model. Okay, so this included distribution, so we can write on this y given x. Well, okay, so the only difference between classical linear regression model and classical normal linear regression model is basically the normality. So later on when I write on this, basically we already imposed the normality assumption on error term. So including the first four assumption, which we use to derive the Gauss-Markov theorem, to talk about the OS estimator. Okay, so talk about OS estimator. So now the fifth assumption, we have distribution assumption for this one. Okay, so essentially we got now this one. So now we can discuss a few things with this. Okay, so with this one, so now we're on this assumption. So now we're here, we're looking at this. Okay, embedding the fifth assumption on the error term. So now the model can be written as this. So now we can see that, okay, since beta is given as this, okay, all right, so let's say we know, so in the this, beta hat, given x. Okay. So remember beta F has business like this, right? X prime, X inverse, X prime Y. We all know this. And written as this is a matrix A. I'll get the full notation on some notation convenience. So this is equal to AY. And we know A is basically considered of given X. This X can be regarded as deterministic. So essentially A is a linear transformation of Y, which we already know, right? So that's the linear unbiased estimate. That's the untransformed Y. So here we can see that given this, Y given X is normal. Now apply a matrix A based on our earlier discussion. This is still bivalent normal, right? So here, beta, remember beta is a linear function of Y. Y is given on this assumption is following this. So therefore, this will also follow a normal distribution. Bivalent normal with degree of not n. I think here should be P. Okay, I'm sorry, this should be K. Degree of freedom K. Okay. So here will be equal to A X beta, and this one will be sigma squared A I N transpose. Okay. So again, just utilize we utilize one of the multinomial property. This is A, remember beta, X. That's basically this, okay? And here we know that because beta is unbiased, so AX has to equal to I, which is pretty difficult to prove because it's A is X prime, X inverse X prime. So times X, all this is equal to I, okay? So in other words, to return this way, so here we're going to get, so simplify this is basically equal to which should not be surprising to you. Because we already derived from the Gauss-Markov theorem. Beta, OS estimated beta will be unbiased with variant covariance matrix given as this, right? If you remember this. And it's also very easy for you to derive, okay? Because what's A? A is X prime, X inverse X prime. Times I, and times this again. So this will simplify to this, which is not surprising, okay? So here, given this, so now we can see that so now beta also follow normal multinomial distribution. Obviously here will be dimension will be k because we only have k parameters, right? K number of parameters. Okay, so is that clear here? So originally we assumed that the observation we have n observations. So we have n observations. But when we apply this regression, since we have only k expected variables, therefore the order estimator of this regression is basically with dimension of k, with mean equal to beta, variance equal to sigma squared x prime x inverse as we know, and also normal distributed. That's not surprising, okay? That's not surprising. So now, furthermore, because beta is normally distributed, so again using the bivalent normal. Remember, beta is a multinomial distribution, so here's the degree of freedom k. So we can, for any linear combination of from here, so from here on actually we can further derive this. Let's say if we suppose we have now it's a linear for any vector, okay, which is not equal to 0. We don't want to go 0 vector because 0 multiplied by beta that will be 0. However, then we don't need to talk about it because it's a 0. Okay, so for any P P, okay, later on I will explain what that. Okay, so for P, so obviously P is larger than 1, larger than or equal to 1. So now we know we can think about this linear combination of beta. Okay? So if we, this is for any non-zero vector, or sorry, for any non-zero matrix, this and this becomes like a linear combination. Okay, linear combination of Earth's estimator should be also following a bivalent normal. Because this is a bivalent normal, right? It's a bivalent normal. Then we apply a matrix here. This is still following normal distribution. And so here, so because of P, this is P times K, and beta is K times 1, so therefore here is a P, okay, degree from P here, okay? So P will be here, P. And so here, this one will be equal to alright, so the mean will be equal to this matrix times beta, and the variance covariance matrix will be equal to this, okay? So this sigma squared is basically scalar, we can take it out, okay? So here, this is the matrix, this is K by K matrix. So after we apply this one will become like this, okay? So again, we just keep using the nice property of multivariate normal distribution. So we start with this, enclosed error term in normal distribution, and then we realize beta always estimated linear combination of y. So again, this will follow a multivariate normal distribution here. So since beta had been following normal distribution, then we can find a kind of linear combination of estimated, OS estimated, and they still follow multi-normal distribution. Okay, and obviously the mean variance will be changing accordingly based on the distribution right here. So any question for this? Any question for this? For this little bit, you know, for this one. So now you may think about, wow, this is a little bit difficult to understand. So let's take it like more simple. For example, let's think about, let's take this one, okay? So this is, that's equal to okay, so this is will be, let's look at this one, let's look at this. Let this matrix gamma being basically this is what is 1 times k. 1 times k. Okay? So there's only one row, and the nice thing about this is that only the jth term, this is the jth. The jth element is equal to 1, or the other will be 0. Think about this k, think about this is a, k is equal to 4. You have 4 exponent variables, okay? Then let the j equal to 2. So in other words, the second element is 1, the other will be 0. What does that mean? What does that mean? Basically, if we apply this matrix to this, what is this? This is basically given this one. This basically is equal to so in this case, if like this one, so then if you combination this basically it's okay, basically this one. So now we just look at the J's private estimate. This one. So now given this, so basically this says that this beta J hat, in this case, so from here, so we know that this beta J, based on our assumption here, so essentially this is the normal distribution, since P is equal to 1, right? In this case, P is equal to, we can see that P is equal to 1 here. We just look at this one. So this will be a normal distribution given that this is equal to be specific is basically the diagonal terms of the JJ term. So in other words, if you look at this one, if we apply here, so in this case equal to this, right? So if we apply this particular vector, it was estimated. So we know that this guy is basically equal to beta J hat. And if given following the property here, then given x, so this beta, the jth element of OS estimator follow norm distribution with the mean equal to the true beta j, and the variance conversion matrix basically is equal to the jth diagonal term of the variance conversion matrix you estimate from the real one for that, okay? So here, okay, gamma can be, let's say, this represents basically linear combination of data. So later we come back to illustrate a more example to understand what this gamma is, and this basically relates to the hypothesis testing. In this case, we want to test whether the J's estimated is significantly different from 0 or not. Does that make sense? Supposing you only have 4 exponent variables, and J is equal to 2, the second parameter. And here we are looking at whether x2, the second exponent variable, x2 has a significant effect on y after you run regression. And this is basically that, okay? So essentially imposing the restriction here, okay? With this factor here, okay? So as I said, this is a little bit abstract at the beginning, but later on when we look at some examples, then you have a better understanding what this, why introduce gamma here. So this is related to hypothesis testing. We're quickly going to discuss here. Okay. So now, given that, okay. So now it's pretty easy for you to see that. So for this one, we took a lot of time. Gamma to stand for this. So for easy, okay, so if we impose linear transformation gamma on the OS estimator, then this will be following the linear transformation, will be following normal distribution, means pretty easy to understand, with variant conversion like this, okay? To be simplified, we read as a big sigma. Big sigma is equal to gamma square, sigma square, lowercase sigma square times gamma, then x prime x inverse, then times gamma transpose. So this will be sigma, okay? So sigma, we know that it's a variance conversion matrix. If it's a variance conversion matrix, then it's positive semi-definite, as we just discussed at the beginning. As a result, we can calculate the square root of this. Okay, so in other words, there's a square root loose way. Okay, so we can find basically from here we can define, because of positive semi-definite, we can define the loose way to this one. Okay, so basically that's we can take square root. We can also take inverse. Basically, look at the this inverse. Okay, so these are all defined, well defined, and we're going to quickly use this for this one. Okay. So given this, okay, so we're coming back to this one. So here, given this one, so now I want to do standardize. I want to do standardize. So what's the standardization here? So let me define Z. Obviously here Z is vector, okay? Let's define Z. So Z is basically standardized what doing like this, okay? So Z defined as oops, this is a little bit okay, Z. All right. So remember, this is this one, right? This is a new random variable, comma, beta hat. So the mean is this. So the mean can take a square root of the variance covariance matrix with this big sigma defined here. Okay. So this is a typical Z statistic, right? So here we know that for this one, we know to find this one, then we know Z given X will be following so since it's standardized. Since it's standardized, then obviously it has zero mean and unit standard deviation. Obviously, this unit standard deviation basically is a identity matrix. Does that make sense? Is that clear here? So now we keep doing this. So define this one, so define first one. So now I define another one. Define W and Z prime Z. Okay? So it's kind of like Z squared. So we know that if Z squared has to be chi-square distribution, right? We already discussed this. So now if you write out this, what's this one? This is basically returns this. Okay, so it's basically like this. Okay, so that's what it is. If Z prime Z right in this one, so essentially this equals this. So kind of like a square. Or it's a matrix span, basically. This is the transpose times the inverse of this variance covariance matrix, this one, and multiply this again. Okay, so this will be, and we know that this W given X will follow chi-square is derived from P. So why is P important? Because so P is this one. P is the dimension of this linear matrix we are going to apply to the earliest estimate. Okay, so P is this one. So this will be the so any questions so far for this one? So just think about a scalar case. Okay, here a little bit abstract because we're talking about the matrix one. But if you think about scalar case, it's probably much easier to understand. So if a scalar that's P equal to 1, so basically this is equal to a sigma squared divided by a square root of variance covariance matrix, which is then as normal distributed normal. X minus B divided by sigma squared. That will be standard normal. This is basically Z squared. And obviously it's chi-square distribution. And further, you also noted that in those distribution, Z given X, W given X is in Gaussian normal distribution. Auto distribution does not depend on X. Okay? So as a result, when we look at the unconditional, okay, if you look at this one, then we also can see that because when we look at this P distribution, okay, 0, IP. So if we look at this, this distribution does not depend on X at all, right? This distribution doesn't depend on X. So therefore, Z, if we unconditional, it's also, oops, okay? And W. Okay? So we can get rid of the conditional distribution. Because those distribution does not depend on X at all. Okay? So clean X is this distribution and unconditional still this distribution, okay? So this will be the situation here, okay? So far we look at this one. But we all know that empirically, a lot of time we don't know what the sigma square is. Now this is what the sigma square. This sigma square is the distribution, the assumed variance for the error term, which is scalar. But a lot of time we don't know what the sigma square. So in other words, if we have to estimate, now if sigma square unknown, we have to estimate it. So how we estimate it? This one, you're using sample square, right? We're using sample square, okay? So all the time, if we have to estimate it, so we estimate this one, we come up with this. So you use head is the estimation, and this one is the sample variance. Okay? And this is equal to right, this is we just to estimate everybody know, right? So the sample variance is basically this using prediction residuals. Okay, so we have the sum square residuals, right? This is sum square residuals, then divided by degree of freedom. Because this is what will give us unbiased estimate. This is one already you ask you to show in homework 0, right? We calculate the sample. So here this is sample variance for this prediction error. Okay? So here we only have to estimate this one. So now with that we have to, since we have to estimate this sigma square, then so here, all right, so here we're going to see estimate this guy, okay? So we estimate this guy. So now we replace not a scale. So here we're going to replace this one. So here we replace sigma hat. Okay? So sigma hat will be defined as, we can estimate this. Okay, so this is notation convenient. So you can compare this sigma versus this big sigma versus big sigma versus sigma hat. The only difference is that we replace this lowercase sigma square with this estimated. Remember, this unbiased estimated for this guy. Okay, is that clear here? So now again we can do this one. So now essentially what we're going to see this one, okay, so Z is not Z anymore. So here we define so-called T distribution. Okay, so now we have T. The T we have defined T. Now okay, so we define this T. So notice the difference between Z and T, okay? The difference is that we basically replace this variance covariance matrix with estimated variance covariance matrix. The estimated is because of this. We have to estimate sigma squared. Okay? So this will define this one. And this one you know that t given x will follow t distribution. Okay, so this is for p equal 1. For p is larger than or equal to 1, so now we define so-called f statistic. Similar to this term, okay? Similar to this term. So here, what we are going to do this 1 over p, just for degree of freedom here. Okay? So it's kind of similar to this W, but now the difference is that, okay, we replace this variance convergence matrix with estimated variance convergence matrix, because we have to estimate this guy, this guy, then divide 1 over P. And this one actually, we see that F given X will follow the so-called F distribution. That's the degree. So it's F distribution. Remember, chi-square is basically square of normal. So it's F distribution. F distribution is the ratio of two chi-square distribution. So here you can think about this as a this F statistics here is basically the chi-square distribution degree of freedom P divided by chi-square distribution A minus K. Okay, so that's F statistic here. So now let me be a little bit clear here. So when we know this unconditionally, okay, this is Z, unconditionally this statistic will be also normal distribution. This distribution W will follow chi-square distribution. But when we have to estimate this guy, so this sample square, okay, this is we're using sample square, right? We need sample variance to estimate this. And this one, the sigma square, depend on X. Remember how we get this sigma I, epsilon I, prediction error? The prediction is a y minus X, beta hat. So this guy depends on X, okay? So therefore, even though conditional X is a T distribution, but unconditionally, this T is not necessarily following T distribution. Because we know that this guy, this distribution depends on X here. Okay, remember what we estimate here? Okay, here, depend on X, okay? Likewise, for F, same thing, if we unconditionally, this statistic may not be following the F distribution. Because we have to estimate this term, and this term depends on X. Okay? If you a little bit confused this one, because this guy is equal to, it's pretty easy for you to write. And so here you can see that's pretty clear, right? So this will be the whole thing. This term is dependent on X here. X will affect this sigma square head. As a result, this guy will be dependent on X. Okay, so this guy will depend on X. Okay. So you can see that, okay, so we didn't derive this in very detail, but at least I give an idea. So essentially here you can see that this will be commonly used to test statistics in empirical access. Z and W statistics, Okay, Z studio is normal distribution, W is chi-square distribution, and these will be valid when we know the variance of error term. But that's the only ideal situation. Right? In real world, we have to estimate this guy. As a result, we probably refer more to the T step and F step. Okay? So again, this is depending on the dimension of this gamma matrix. Okay, so whether P is equal to 1 or larger than or equal to 1. So now after we do this, okay, so we can do interval estimation and confidence interval and so on. Okay, so I just give this discussion. We can do, given this, after you know the distribution of the beta, right? Since we know the distribution of a beta OS estimated, then we can form some hypothesis, and basic hypothesis basically imply restriction on the beta, estimate beta. And basically this restriction will be captured by this gamma. And with gamma we know, depending on whether we know sigma square or not, we have variance distribution here. So we have a normal distribution or T distribution for the single restriction, or if we have multiple restriction, you know, P is larger than 1, larger than or equal to 1. So we have either W statistic or F statistic. And we all know the distribution. Then confidence intervals are easy to form, right? Later on, you already know the distribution, then we can, given the significant level, you can look at the confidence interval and so on, okay? So I just skip this thing, okay? So any question for that? Any question for this? Okay, so then from here, we can quickly do interval estimation, significant test, and so on. So give this in here, then you can look at the like a confidence interval if you want. Also, you could this confidence interval, you can look at a confidence interval. Also, you can testing significance of the parameter estimate and so on. Okay, so that's basically the general setup for the hypothesis testing. And later, you can also look at the type 1 error versus type 2 error. Remember, this is all the things of the type 1 error. Given significant level, that's type 1 error. And then type 2 error is basically we want to check the power of the test. Okay, in other words, if the null hypothesis is not correct, then how your estimate will be evaluated based on the alternate hypothesis. That gives you the power of the test which we discussed in day 1, day 2, okay, in the class, okay? So I kind of skipped that one, so let me just help you have a little better understanding of this gamma here. Because gamma right now is pretty abstract. Okay, so here just give you the setup for how you do the hypothesis testing, because we need to know the distribution of beta, then depending on different scenarios, we form the restrictions that are basically captured by this gamma. Then combination of gamma and beta, that's basically give us the testing and so on, okay? So for hypothesis testing, let me keep some. Okay, let me just erase this part, leave this part on. So this general setup of the hypothesis testing, linear restriction case. Should be so-called general linear hypothesis. Okay, so some are basically linear restrictions. In other words, free linear restrictions on parameter estimate. So now, this is null hypothesis. Okay? Obviously, this is P, right? P degree of freedom, P restrictions. So now, alternate hypothesis will be not the same. So we will have a two-sided test. Okay, that's common, right? That's common setup. Now hypothesis is gamma beta equal to 0 here, and the alternative is not. Okay, so this is two-sided. This is two-sided alternative, so this is two-sided. Two-sided alternate hypothesis. So now here again, there'll be two scenarios here. One is single linear restriction. In other words, gamma is 1 times k. Okay? That is right. That is basically I. Gamma is 1 times k. So in this case, again, depending on this A1, if known, then we basically get the Z statistics, right? So essentially to reject. Now, if the Z statistics is larger than certain critical value, with significance level of this, okay? That's one, okay? So using N0. So Z is defined this way. So if the Z, because we're looking two-sided test, so if the Z, absolute value of Z, larger than the critical value, C stands for critical value, for this normal distributions, then normal distribution with significant level, you chose alpha, okay? So alpha for two-sided, if alpha is 5%, then basically look at 2.5%, right? 2.5% on the left-hand side, and the right-hand side is a 2.5, which is corresponding, and 7.5%. Okay, so that's basically this is for known. If it's a non-known, that's a rule. If it's not known, then we have to rely on T statistic, that we say here. We have to estimate, okay? So again, reject this one if T statistics okay? So that's a rule, right? So if it's unknown, since it's two-sided test, so that we will calculate T statistics is basically given here, okay? It's given here. So T statistic will be, absolute value of T statistic will be larger than the critical value of this T distribution, with degree of freedom n minus k. Critical value is chosen as alpha derivative. Pretty easy, you know that, because it's a symmetric. T distribution is symmetric, okay? So that's the for single restriction. So now if we have multiple linear restriction, so if we look at the multiple, so on beta, so I P larger than 1. Obviously, we could also regard a linear or single as a special case of 1. So P larger than or equal to 1. But most of the time, we had P is larger than 1. Okay? So in this case, then, again, we have two different scenarios. Depending on whether we know this or not. If this is known, then we're going to reject null hypothesis if the W statistics we define here, okay, will be larger than the critical value of, since the T statistics work squared, that's only 1. Even though it's two-sided, but we just look at it 1, okay? So we're using chi-square distribution, okay, for this one. And if it's not unknown, then we reject null hypothesis if F okay? So that's basically the rule here. So for multiple linear restrictions on beta, then depending on whether we know sigma square or not, we're using the chi-square distribution or F distribution accordingly. And here, just look at a critical value, now given 60%, we choose. Very easy, right? That's basically the rule of thumb for this thing. So, any question for the general hypothesis testing setup here? So let me just erase this, okay? I probably copy this one here. So the sigma. So let's define this. Erase this one. So that's basically the general setup for hypothesis testing after we impose the fifth assumption on the error term. The fifth assumption is the normality distribution assumption. Now, given this normality distribution assumption, then we can derive the distribution of OSS estimator. Because we know OS estimated follow normal distribution, then we can apply linear transformation on this parameter estimate, and they still follow normal distribution. Then as a result, we can derive the test statistic based on whether we know the sigma square or not. Okay? And depending on whether we have multiple or single linear restriction, we have Z statistics and W statistics. If we know sigma square, if we don't know sigma square, then we use T statistics and F statistics for the example for the testing. Okay. So one more thing regarding this, you notice that actually there's a relation between W and Z and F and T. So this is the thing that know that. Okay? So that's why sometimes we can always use multiple situations. So this is easy to see. This is a little more so that because we're looking at multiple linear restrictions, but actually we know that when P is equal to 1, actually the W is equal to W is equal to this. Okay, when P is equal to 1. You can rewrite this P here, W. If you write this here, this one here. Okay? So because it's a scalar, so P is equal to 1. So essentially this is equal to D squared. Just keep in mind. So there's some relation between W and Z when P is equal to 1. So if it's a linear restriction, in other words, if there's a single linear restriction, you could either use W statistic or Z statistic because these two should be the same. And the very reason why I went here, okay, just look at the formula again. Because now it's a scalar, so you can move this one to the scalar by writing this way. I could just square, and this square is basically this square base definition here. Okay, so it's a chi square, which is equal to chi square 1. And f is basically equal to and this is basically equal to t squared, which is equal to f. Okay, so just keep this in mind. Fp equal to 1. So f distribution t squared is basically the same. Now the t squared, if we take a square of the t distribution, that's basically f distribution with degree of freedom. The first degree of freedom is equal to 1. 1n minus k. Okay, so that's the so already defined what's the sigma here and sigma here, so pay attention to this difference here. So that basically gives us the tools, okay, to conduct hypothesis testing for this one. So actually, if you see in real, basically this is basically there's 4 common statistics, and most likely probably focus on this. A lot of time F statistics will be probably most popularly used. If a single, if a multiple, if it's a single, then we use t distribution, because a lot of time we don't know what the sigma square. We have to estimate. Okay, but honestly, we may have to why still even we don't have to estimate sigma square. We still use z statistic, and we'll discuss a bit of the code asymptotics. Okay, we are basically using asymptotics. Okay, large sample theory. But we all know that at the end, all distribution will converge to normal distribution if we have enough large sample. Okay, but here this is for the finite sample situation. So for finite sample, this will be the 4 commonly used t statistic. And most time, probably 1b and 2b will be most relevantly used, because we don't know what the sigma square is, but estimate. So that's why t distribution and f distribution will be probably the most commonly used in empirical studies. Okay, depending on what kind of restriction do we have to probably do. So any question for this? Before I erase it, then I probably give you a little bit better idea of the look at it, the restriction, how we can understand it. All right, if no questions, so now what I'm going to do is that, okay, let's look at some examples of linear restrictions to help you better understand this discussion of the gamma. So as you can see, the thing that as long as you figure out gamma, then pretty easy, remaining is pretty easy. So we estimated, we know, given this assumption, we already estimated, and the gamma is basically the key to form those hypotheses. Okay, so let me just erase this part. Okay, let's look at some examples of linear restrictions. Let's look at example. Just look at general linear restrictions. So a lot of times it depends on the research question you're studying, okay? Sometimes you have a theory for the guidance, so the theory will give you the restriction, okay? but sometimes it's empirical driven, okay? So let's look at some example here. Suppose we have a model of investment, okay? The model like this. Okay, so the model like this, okay, so this is the one. Suppose we have a model of investment, big I stands for investment amount, okay? Which is okay. So capital I stands for investment. Small I stands for normal interest rate. Pi stands for inflation rate. Okay. So just simple model like this. Okay. Suppose you start some economics and you know that investment is related to the normal interest rate and the inflation rate. Okay. So here we don't have any restriction here. Okay, that's a model, general model here. Another way you could also write this like this, okay? Alternatively, another way this way, let's say this is model specific one. Another way to write this is like kind of similar. There's another way to formulate this model. So what does it mean? This means what's IT minus IT? That's a normal interest rate minus inflation rate. So that's basically real interest rate, right? So real interest rate. So this another way to model is basically link the investment, level of investment, to real interest rate and inflation rate. Okay? So this is another way to model this. So this is another way to model this, okay? So this would be this alternative way of formulating this. Now, given this, let's look at some, suppose we have some theory. Theory was that okay, maybe investor care only about real interest rate. Okay? So in other words, which implies that okay. So here, this is a sort of a theory that care investor or care only about real interest rate. Okay, so that's one of the theories. Suppose you want this is theory. Okay. So it's pretty easy for you to see that 1 and 2 are kind of equivalent to some extent. Obviously, but the interpretation of coefficient will be different. Okay, so depending on how you specify the model, those coefficients, even though still in the beta 1, in beta 1 versus in equation 1 versus beta 1 in equation 2 have different meaning, right? Because we know that beta 1 equation basically captures what's the impact of a normal interest rate on investment. On the other hand, beta 1 in equation 2 captures what's the impact of the real interest rate on investment. Okay, but these are still kind of equivalent specification. We still care about this. Now, here we look at the one particular hypothesis or some theory. Suppose you want to test maybe managers or investors care only about the real interest rate. So investment will be only depending on the real interest rate. So obviously, so what is the restriction being imposed here when we're testing this theory? Right? Clearly you can see that 3 is a narrow version of the general model. It's pretty clear, right? So for that reason, this narrow version sometimes called a nested model, because it's just only kind of subset of the variables this. Okay? So here, if we have this theory, this is the hypothesis, basically we already impose some restrictions here on the parameters. So now the question here that what restriction have we imposed? So again, so this one to specify which restriction we impose here, it depends on the original model specification. Okay? For example, let's look at 2. Suppose 2 is your original model specification. Now, from 2, if this is based on 2, suppose 2 is the original model. Okay? So now based on 2, what's the restriction here? We'll compare 3 versus 2. That's pretty easy. We know that compare equation 2 with equation 3, if we want to test this particular hypothesis that managers, when making investment, they care only about the real interest rate. That's a hypothesis, right? That's a theory. I'm sorry, that's a theory. But that theory basically imposes a restriction on the model. So what particular restriction we're imposing here? So now based on the, if 2 is the original model, that's very easy. So given 2, so for 2, so essentially compare these two, this says that if that's the case, delta is equal to 0, right? So that's a hypothesis. Is that clear here? So that will be the null hypothesis you're going to test here. If your original model is specified as in 2. Does it make sense? So here this is the model based on the hypothesis, based on this theory, so we know that if investment only depend on real interest rate, then this will be delta equals 0. Now a little bit challenging this one. What if the original model specifies as 1? Suppose this is your original model. You model this like this. So what would be the general linear restriction you can formulate based on this particular theory? Anyone have a try? So what would be the this is, this will kind of like move away from this abstract discussion and go to some empirical, right? A lot of times you have some theory, you know, the test. It's just theory, this is the story you want to tell, right? The theory is that you want to do some empirical study, you tell in theory, this is the story you have to tell the audience. But there's a question here that, well, with the theory, of course, there's a restriction. You have to formulate. So the question here is that, what is the restriction you can formulate here? If a model, original model specifies this. Anyone have a try?
What's the main theory again? Now, I just want to take I just want to take the main theory, like rating the main theory that you said again. Like the managers don't really base their investments. They are more, you consider real interest rate than inflation.
Yeah.
That's the theory.
Yeah.
And so we want to formulate a hypothesis based on that theory.
Yeah, see, remember. Okay, this is theory, right? This is the, suppose this is the, you want to tell a story that the manager, when making investment, they only care about the real interest rate. So that's basically the story you want to tell. You're going to test it, right? you're gonna provide empirical test to show if that's the case. I said, if you specify model, original model like this, then very easy, it's very straightforward, right? We know that given your original model specifies as 2, then it's very easy, okay, then obviously inflation rate should not have impact on the investment after you control for real interest rates. So therefore, it's pretty easy, given 2 as the big model. Remember, this is a narrow model, so it's clear. We just need to test beta 2 equals 0. So we need to do is basically get data around this regression and test whether beta 2 is equal to 0 or not. So if beta 2 is equal to 0, we can reject this null hypothesis. That basically you provide evidence that EM managers, when making investment, they only care about real interest rates. Right? That's how you do it. Does it make sense? So this is very straightforward. If you specify your bigger model, or wider model, broader model like this specification, so this is easy. You just test the beta 2 equal to 0. And you run regression of 2, then test whether beta 2 is equal to 0. Okay? And then I can explain what is gamma here, and so on. Okay, but let me phrase this first. Then come back to look at gamma and the beta, okay? So, now my question to you here is that suppose your model starts with 1. This is your broader model.
So can it be inflation has no effect on investment?
Because here, if you look at this one, beta 2 equal, you want to say beta 2 equals 0? But here they say that, okay, this means that the nominal interest rate, here remember the testing is on the real interest rate. Manager care only about the real interest rate.
Okay.
So it's not like a beta 2 equals 0. Clearly it's not, right? It's not. But beta 2 equals 0, if you start estimating model 1 and testing whether beta 2 equals 0, that basically says that the manager care only about nominal interest rates when making investment decisions. So how we do this? This is known as so again we have to impose some. Okay, so here this one is this, okay? Beta 1 plus 2 beta 2 equals 0. That's the expression. Why? Why? Because if this is true, what happens? Okay, let's look at model 1, okay? So model 1, basically for model 1, under this one, model 1 will be beta 0, beta 1. So here this will have beta 1. Right? If this is a restriction, so the equivalent is beta 2 equal to minus beta 1. Okay? Substitute beta 2 minus beta 1 into restriction, okay? So under this restriction here, right? And now, that's a green streak, right? That's a green streak. So this shows that if you specify model as 1, specify the broad model as equation 1, then the testing of this hypothesis will be equivalent to saying that beta 1 plus beta 2 equals 0. Okay? Does that make sense? Hopefully, does that convince you? Okay? So obviously this under, if you this right, under the now. Now this beta 1 plus beta 2 equals 0. Does that make sense?
Can you go over?
No, okay. So remember this is model 1. So now we have to see that what's the relation between model and 3. Right? Forget about 2, because 2 is another specification of the broader model. So here we're looking at the broad model being expressed as a 1, and we're going to test the hypothesis which corresponds to model 3. So my argument is that to link 1 and 3, this implies beta 1 plus beta 2 equals 0. That's a restriction consistent with this story that the manager or the hypothesis manager investment decision only depend on real interest rates. So why is that the case? On this restriction, so we can rewrite beta 2 as minus beta 1. So if beta 2 is equal to minus beta 1, then equation 1, right? Equation 1. We replace beta 2 with minus beta 1, and we combine this term. This is what? This is the real interest rate into this one. Does that make sense? So that's what I'm trying to say there, okay? So for this particular hypothesis, and if it's equals to model 1, then the corresponding restriction should be beta 1 plus beta 0 plus beta 2 equals 0. Is that clear? Does it make sense to you? So in other words, so if you estimate model this, when you run regression of investment against the normal interest rate and inflation rate, then to present the story, to test the hypothesis, you really want you to test is basically test for whether beta 1 plus beta 2 equals 0. Okay? So this is one important thing I would like to emphasize, okay, on empirically. So see, you have the same story, but they can have different ways of formulating restrictions, depending on how you specify your sort of the broader model. Okay? So don't be confused, don't be misled, okay, because the form of restrictions are the same, are not the same. So these are testing two different stories. Now we are testing exactly the same story. Right? Is that clear here? We are testing exactly the same story that managing investment only depend on real interest rates. So that's the thing here, okay? So now, if it's clear here, so let's formulate what is gamma. What is gamma? Remember, right? This is the general setup, right? So in this particular model, what is gamma? What is this gamma 0 on the right hand side variable? Okay. So here, what is beta here? Beta is pretty clear. Beta in this case, beta in this case, in any kind of model here, no matter what the beta equation model 2, right? Beta is basically the beta 0, beta 1, beta 2, right? We have 3 parameters. So beta is basically this one. Beta 0, beta 1, beta 2, beta 3. So these are 3. That's beta no matter what you look at it. Equation 1, equation 2. So what will be the gamma here? So here, in this case, gamma. So for this one, what's gamma here? Gamma will be 0, 1, 0, right? If you look at the beta 2 based on this one, okay? So what's the gamma 0 here? So it equals 0. So here you can see that it's a single linear restriction. P, because P is equal to 1, with gamma just a vector. Right? P is equal to 1, so it's a single linear restriction. Okay? So you could easily use Z to this or T depending on whether you know. Now in this case, what's the gamma here? You can remember, this is one, beta 0, beta 1, beta 2, right? So here, again, gamma 0, is equal to 0. Does that make sense? Yeah. So this is how you formulate this. So that's one example here. Any question for this? So this is the one, okay, this is the one theory we want to present, okay? Let's do another exercise. So suppose this is story number 1. Maybe let's say look at the story number 2, theory number 2. Let me try to not use S because we already used S before assumption. So let's use theory number 1, T1, care about inflation money. Let's then look at testing another theory. So I want you to figure it out. Suppose managers in investment just care about inflation only. Suppose this is theory. Suppose managing investment depend only on inflation rate. That's one theory. So how we do this? Well, so the model is pretty easy, right? In this case, it will be just like IIT equal to beta 0 plus beta 1. Oops. Equal to beta 1 pi t. Okay, so that will be a model like this, right? Essentially, this is the model you have in mind, if you want this one, right? So if we care about inflation rate only, then this will be a model like this. So now the question here that if you have this model, so what's the restriction here? What's the knob here? So if you special model as 1, so now it's pretty easy. If you model special this one, then what's the tacit thing here? Oops, sorry, this is my mistake. 0, 0. Oh, I was confused. Okay, because beta 2 is the last one. Okay. That makes sense? So it should be 0, 0. My mistake. Okay. So for this null hypothesis, now it's very easy for you to formulate. If you start with model 1. If you care about inflation rate only, then in this model specification, the null hypothesis will be beta 1 equal to 0, right? So therefore, the gamma will be 0, 1, 0. That should be corresponding to this general linear restriction here. Make sense? Okay, so now let's look at number 2. Let's suppose your model specifies a model 2. What's the null hypothesis here? What?
Either one is not equal to 0.
Uh,
I'm just guessing. I'm not sure. I'm not sure of it.
which one did?
Either 0 is equal to 0.
What?
I mean, you can't add beta 0 and beta 1 is equal to 0. So
So when you have this, you have beta 1 equals 0. Right? Do you need anything else? Is it enough?
I thought if it's If it's a single independent variable, it's greater or less than that kind of situation, so it's equal to or it's not equal to. Is it not hard?
Mm-hmm.
Because you are testing whether, because it's only one variable, whether it influences it or it does not influence it. Is that like the general understanding?
Uh-huh.
And so, if first hypothesis is beta 1 is equal to 0, then now the second one will be is not equal to 0.
So better than not equal to 0, you want to say, right? You want to say that better than not equal to 0, that's what you would say if you care about inflation rate only.
Yes.
Okay, but if testing beta 1 equals 0, the model is basically this, remember, model is like this. The model will be like this, right? Beta 0 plus some coefficient times inflation rate, and this. So here we're going to see whether beta 1 will be equal to 0 or not. You know, care only about inflation rate only, but it depends on whether beta 1 will be significant or not. If you model this one, right? But here we're looking at this. So here we're looking at a restriction, we look at a bigger model. We look at the more broader model here. So from here to derive here, or from here to derive here, you just need beta 1 is equal to 0 or not. You have to input beta 1 equals 0. Then we got this model here. Obviously your question here is that, okay, what if beta in this model you specify estimate model 4? I think your question here is that if you estimate model 4, then you are going to consider whether beta 1 is equal to 0 or not. Because if beta 1 equals 0, that means this hypothesis is not right? Because manager investment does not depend on inflation rate. Okay? You know, as I said, this is depending on how you express the model.
Okay.
You understand here? I get your point. So if your original model is like this, then your hypothesis you care about inflation rate only, you're right. You want to test whether beta 1 is equal to 0 or not. Because beta 1 equals 0, that means inflation rate has no impact on managing investment. Okay? But that's what I'm trying to emphasize here. Suppose your scoring model is this. Obviously, you do not approach this time, it's not usually when you estimate this, you cannot just like focus on one control for other things. So that's for more realistic situation that you approach special more problem model and not give a particular story here. So how you go from the more broad model to the narrow model. So of course you already embedded some restrictions here so that you can simplify those or parallel terms. So these are the restrictions we look at here. Okay. Does that make sense? Does it make sense to you here? So now, if the original model specifies 2, and here obviously this testing will be beta 1 will be equal to 0. Okay? So if beta 1 equals 0, obviously this will be the we reduce the model to equation 4, right? From equation 2 to equation 4, if this is the case. Right? So in this case, you can see that, okay, now in this particular case, assume that the both null hypotheses will be the same, no matter which one you start with. Okay? So, given here, and this will be the same. So we're going to write it. Okay? And we could also have one more type. So for example, like we can see hypothesis theory 3, so care about nominal interest rate only. So what if this is theory? So manager investment depend only on nominal interest rate. So in this case, obviously the model we're gonna see, implicitly we're gonna estimate will be this, right? So let me name model 5. Okay, model 5. So again, depending on which model specify this, so for the models that start with 1, so now hypothesis will be here will be beta 2 equals 0. It's pretty straightforward. Okay, so here gamma will be 0, 0, 1. Okay, it's very easy for you, right? It's pretty easy for you to see here. And now if you model start with, this is a model to specify here. Now hypothesis here will be if your model is number 2 will be your hypothesis. Okay, so I can run fast if you go starting with model 1 because it's pretty easy, straightforward. Beta 2 equals 0 is very, very straightforward. So now crossing here that if you start with model 2 specification as a broader one. So what's the implication? How you can derive this one? It will be beta 2 minus beta 1 equals 0, right? How you do this? Just separate this term out. Combine inflation rate, pi. Okay? So it's pretty easy, right? Beta 1 IT minus 1 beta IT, also beta 1 pi t plus beta 2 pi t. So combine inflation rate, beta 2 minus beta 1. The testing will be beta 2 minus beta 1 equals 0. Does that make sense to you? Or do I need to write it out? So any question for this? So if you start with this model 2, then to test whether this particular theory is true or not, measure care only about the inflation, nominal inflation rate, or sorry, nominal interest rate, then this model 2, given this theory, implies that null hypothesis will be beta 2 minus beta 1 equals 0. So now, in this case, the gamma matrix will be 0, minus 1, 1. Okay, on the right hand side, the gamma 0 is always equal to 0. Because here we're testing basically single linear restriction. So in each case it goes 0. But now the gamma matrix changes, right? Now the gamma matrix becomes 0, minus 1, 1. Keep in mind, right? Beta is a beta 0, beta 1, beta 2. So any question for this? Any question for this? Okay. So this is a simple example. I try to illustrate two cases. Okay, two important parts in terms of empirical study. First of all, okay, each story you are telling basically involves some restriction scheme. Okay, you're testing this theory on some basis, testing some, in terms of empirical, you're testing the different restrictions. That's wrong, okay? So, given this, obviously, this already here, this is kind of like the blueprint, right? What's the you use? It's easy, you get a data, you estimate model, and you get this, then basically combine restriction and figure out whether, at the end, this restriction will be, this hypothesis of the restriction will be supported by data or not. Okay, that's basically testing of the economic story. That's one. That's a general setup, how you implement this in practice. Second one, I think I want to like this a little bit subtle here is that, so the way you specify restriction can vary depending on your original model you start with. Okay? So don't, in this case, no matter we start with model 1 or 2, the same null hypothesis, so that's probably, it's convenient. It doesn't matter whether you express in model 1 or model 2. But a lot of times, even you're testing the same story, because you specify your model, starting model different ways, and the corresponding restriction will be different. Okay? But don't be misled that because you're testing different restrictions, so you're testing different stories. That's not necessarily the case. You have to be careful in terms of what is the starting model. Okay, as you can see from T1 and T3. You can look at the testing of T1 versus T3, you can see that, right? In both cases, the two null hypotheses will be different, depending on whether you start with model 1 or model 2. However, these different restrictions are testing the same story. These two different restrictions are testing exactly the same story. Okay? So you have to be careful. So it's sometimes it's a kind of like an empirical pitfall you may easily fall into, especially if you have some theory in mind. You really have to be careful in terms of the, especially in the starting model. And given the starting model you derive, what would be the corresponding restriction given the story you're testing for in the paper. Okay? Is that clear here? So while here also it's, how you way to figure out what to write out those restrictions here. And here a lot of time probably it's relatively easy because these are like single linear restrictions. So probably at the end you just need to combine the terms and do that, okay? And substitute into the equations and probably can compare the testing accordingly. Now the third point I want to make is that regarding this example here, as you can see that regardless whether model 1 or equation 1 or equation 2 as a starting model, you can see equation 3, equation 4, or equation 5, this is equation 5, right? These three equations, each of the equations is basically a subset of the equation 1, equation 2. So relative to equation 1, equation 2, equation 3, equation 4, or equation 5, each individual of the three questions is basically a subset of the original model. So these are called nested model. Okay, so this basically you can see what 3 is a nested model of either 1 or 2. Likewise, 4 is a nested model of either 1 or 2. Okay? However, 3 and 4, if you compare 3 and 4, they are non-nested. They are non-nested models. Okay? So you cannot see that you cannot nest the model 4 into model 3 or vice versa. Similarly for the other things, okay? So that's all the important thing in empirical. Sometimes you may testing nested model, sometimes you may testing non-nested model. Now for nested model is relatively easy to deal with. But sometimes you may be testing non-nested model, then you may sometimes need to do a little more advanced method to deal with them. Okay, but again, we don't have time to discuss about the non-nested model testing. So a lot of time we'll focus on discussing the nested model. Okay, so is that clear here? So I want you to be aware that, okay, so 3, 4, and 5, these are non-nested to each other. So now the model contains the other, and so on. So let's do that, okay? Alright, so this is the general restrictions, okay? So this is so far, this is like a simple example here. If you don't let me erase this, do you need to copy down or take picture of this before I erase it? Okay. So I still keep here because I think this will be kind of like the guideline for us to do this. So I will make again. I'm still using this model a little more complicated. So let's look at the multiple linear restrictions. So far, we only look at the single linear restrictions, right? So now, for the reason, I'm specifying, more general, maybe controlling for something else. So let me introduce, so now you have a more general model here. So let's name it as equation 6. Okay. So that's equation 6. Okay, so now instead of this model, so I realized maybe this model is too limited, so let me add something else, okay? So this is equation 6. So what's here? So here, okay, I'm looking at, again, looking at firm investment. So now this is the nominal interest rate, inflation rate, this is GDP level, okay, log level, okay, so we can look at a log of GDP, then T stands for time trend. Maybe assuming that, over time, maybe investment grow over time. So time trend. So now here we have 5 parameters, right? We have 5 parameters, there's be more, so in this case, I want you to spread this one. Okay, so here beta, obviously beta, as you can see that, beta here will be 5. Okay, let's keep on. So here beta is basic. Here will be beta 0, beta 1, all the way to beta 4. So now it's a 5 by 1 matrix, right? The 5 by 1 factor. So it will be 5 parameters. So here I want you to do some exercise to have to better understand here. Okay, so how to do gamma here. So first of all, I want you to specify what is gamma and what is this, okay? So let's do some exercise here. So this is let's do some exercise. First of all, let's do let's say beta j is equal to 0. So j can be 0, 1, 2, 3, 4, okay? So let me make it a bit easier. Maybe just say beta 3 equals 0. So this should be easy. What's gamma here? Gamma in this case is pretty easy, right? It's basically equal to, so the null hypothesis, these are null hypotheses, okay? So these are all nesting hypotheses corresponding to different models, okay? So beta 3 equals 0 basically said, okay, firm investment decision does not depend on GDP level. Okay, good, right? That's the theory, right? So in this case, the gamma is pretty easy. Basically, 0, 0, 0, 0, 0, 1, 0. All right? So gamma 0 will be equal to 0. So I did this for you. So single linear restriction. Okay? So that's corresponding to this gamma. So now let's look at B. Let's say some hypothesis we'd like to see. Let's say beta 1 equals beta 1 equals beta 2. What does that mean? Well, you can see that, well, inflation and interest rate have the same impact on investment, right?
Yeah.
That's basically what it is. So that's one. Obviously, when you specify this, there's some story, right? You should be able to recognize what's the story behind it. But here, I'm not going to specify this. Okay. So in this case, what should be the gamma here? Okay. So here we are involving 2 parameters here. How many restrictions do we have here? 1 restriction or 2 restrictions? Okay, the testing is that, okay, I say the theory is that, okay, the hypothesis corresponds to this way, saying that inflation and non-interest rate will have same impact on firm investment decision.
The restriction is 1. It's 1 because it's the same.
Yeah, it's still 1 restriction here. t, okay? So here the gamma will be 0, okay, 1, minus 1, 0, 0, 1. Because this is equivalent to beta 1 minus beta 2 equals 0, right? So therefore 0, 1, minus 1, 0, 0. Or you could write this way, or 0, minus 1, 1, 0, don't matter. Because this says that this current from this equation said that minus beta 1 plus beta 2 equals 0. Okay, the same thing. Okay, so essentially you can see that to testing beta 1 equals beta 2, gamma can be written in two different ways. It could be either 0, 1, minus 1, 0, 0, or 0, minus 1, 1, 0, 0. The equivalent. Okay? So this gives you the idea that when you express this gamma may not be uniquely defined. You could write gamma different ways, even though you are testing the same restriction, testing the same theory. Is that clear here? So it's very common that the gamma need not to be uniquely defined. You could have different ways of combining gamma. Yes?
So, because we now assume inflation and interest rates are the same, and so have our restriction has reduced to 1. I was thinking that gamma should be treated 0, maybe 1, 0, instead of
You mean talk about this gamma?
yeah. So my understanding is that most of the time we use 1 for the interaction, right? The 1 represents the main thing that we are trying to find, not the restriction. Where the so like for the first gamma that we had, it was 0, 0, 0, 0, 0, 1, 0.
Yeah.
Yes, and I was using it to just match with the main model.
Yeah.
That's okay. So the first 0 is like beta 0.
Yeah.
And so the 1 was representing the beta, that interaction. And so if we reduce the restriction to, not reduce, but assuming the interest rates and the inflation is combined 1 restriction, and we are rewriting the gamma. Now we should have beta 1, beta 0 being 0, and the 2 restriction being 0, and the main one we're looking for, is it a B3 log being 1? I don't know if it makes sense, but that's how I was trying to really understand it. But
No, I probably don't fully get what you're trying to say. So you want to change the model here? Is that what you mean?
not change, but okay, because the assumption is that now we have the 2 conditional restrictions being 1. If you are rewriting the gamma, then it's going to, those 2 is going to represent, like, we're going to use 1 variable to represent those 2 conditions. Instead of, you're trying to explain that then 1 and negative 1 represents, at the end of the day, 0, kind of. So my understanding is that you have 0, instead of the 1 and negative 1 being 0, then 1, which is the main thing you're looking for, the B3 times the log of.
Let me see, okay. Now, I think probably what you have in mind is basically want to change the model of 6, special restriction model 6, right? You want to combine I know what you're thinking. I think what you have in mind is like basically you substitute this restriction to the model. Yeah, that's a way to do this. We'll discuss a bit later on. Okay. So yes, so essentially that's one particular way. Essentially, like you embed restriction into the original model, then look at the model basis restricted model. Right, look at restricted model, and restricted model what do I equal to 0, right? So in this case, I think we are equal to impose beta 1 equal to beta 0. then basically what you have there is basically you combine. So you're asking more about the investment against the beta 0 plus beta 1, but you have the
Yeah.
inflation plus nominal interest rates.
Yes.
Then you're testing whether this coefficient equals 0 or not. Right? But this one will be slightly different from this because yeah, it's a little bit subtle here, okay? Let me probably save this for next time because we're going to discuss restricted versus non-restricted cell. Because today I don't have time to talk about the F statistic. Okay, so later on, next time we talk about F, actually I'm going to talk about this invariant restriction to the model. Okay, so right now I'm looking at just like given the original model, we estimate unrestricted model. Okay, so this is called unrestricted model, and we know that each narrower model is a restricted version by implying certain restriction scheme. So here we're just starting with estimating unrestricted model, then testing the hypothesis here. And obviously we need to figure out this gamma and the gamma 0 here based on this formulation here. Okay? So keep this in mind, remind me if I forgot. Okay, so we come back to this issue and we discuss the issue here. I think, yeah, it's right, but I don't want to confuse you for the time being because I want to talk about different ways of working at F statistic. Here, so far we all are discussing based on the estimating the unrestricted model, then after figure out this gamma and we form a statistic based on this. Okay? So for you, for me to answer the question in a more precise way, we have to take a deep look at this F statistics and see the alternate way of reformulating this F. Then we come back to this issue. Okay? Yeah, I know what you're talking about. I think yeah, but it's like a little bit faster than. Here, just yeah, you know, I think you're right. You're right. We can do that. We can put. So far, we haven't had a statistical tool to carry out what you want. Okay, is that clear here? So let me put that way. So after next time, after I discuss a little more discussion about this F statistics, then we revisit this. So that's in practice we do have two different ways of carrying out empirical testing. We all know empirical testing is this hypothesis as a base of corresponds some theory or some story you want to present to the audience, right? So, but there are different ways of doing it. Sometimes it's easy, sometimes it may not be. Okay, but this is general. As I said, this is general setup. You won't go wrong, but sometimes it's a bit cumbersome because here you have to go through this matrix operation. Sometimes you may not like it, but I'm telling you this will be general. It can help you deal with even some complicated situation. Now, what you do that if you want invariant restriction to model may not be always feasible to do that. Sometimes, okay. So this will be general. Okay, is that clear here? So coming back to this, okay. So is that clear here? So in testing, this is basically, you know, both inflation rate and the non-interest rate will have the same impact on firm investment decision. So the corresponding hypothesis will be beta 1 equal beta 0, beta 2. And as I pointed out, so there will be two different ways, at least two different ways of formulating this restriction in terms of gamma. Okay, so as I said, gamma can be not necessarily uniquely defined. Okay, so there are different ways of gamma. Okay, so for this one. There's some weird thing. Okay, so there will be beta 1 equals 0, beta 2 equals 0, and beta 3 equals 0. So what does that mean? That means beta 1, beta 3. What does it mean? That means that basically the management decision does not depend on the nominal inflation or output, GDP. Essentially, there's depend on time. That's also you could say, okay, firm investment only depend on time. Essentially, time trend. There's a time trend for this investment. Okay, so in this case, so we have this beta 1 equals 0, beta 2 equals 0, beta 3 equals 0. So in this case, what's gamma here? So how many restrictions do we have here?
3.
You have 3. Okay? So in this case, gamma will be three, at least three rows, okay? So first one will be beta 1, 0, 1, 0, 0, 0. Okay, keep in mind, beta is a 5 by 1 matrix, okay? So this is corresponding beta 1 equals 0. So beta 2 equals 0, will be 0, 0, 1, 0, 0. Does that make sense? And beta 3 equals 0 will be 0, 0, 0, 1, 0. Okay, so here will be 3 times 5. 5 obviously is corresponding to number of parameters, right? So this is what I mean P. P now corresponding to the number of restrictions. As I said, okay, so here previously I derived this, P is general, but now you can see that it's clear. P is basically stand for number of restrictions, based on the model or theory you want to test for. So in this case, what's the gamma 0 here? Gamma 0 will be also a vector. So in this case, it will be 0, 0, 0. All right? So is that clear here? Okay, so now let me just give you one more example here. This is a little bit, we'll suppose beta 1 plus beta 2 equals some constant. So if you want to say beta 1 plus beta 2 basically means that, for the reason, okay, so, and let's make it a bit work here. Beta 2 plus beta 3 equals B. Beta C. Suppose you have this. Okay? So the obviously the story here is probably a bit more a little bit murky, okay, so I don't want to that's a little bit just help you understand how to formulate this restriction here. So now what's the gamma matrix here? So again, how many restrictions do we have here? 3.
Okay.
We have 3 restrictions here, okay? So now this gamma will be, in this case it will be 0, 1, 1, 0, 0, okay? And gamma 0 will be A, correspond this one, okay? So this corresponds to A. Beta 2 plus beta 3 equal A, so it will be 0, 0, 1, 1, 0. This is B. Okay? And beta 3 plus beta 4 equals C. So that will be that. So again, this will be 3 times 5, and this is 3 restriction and so on. Does that make sense? Okay, any question here? So here, okay, hopefully, by those example, I have you probably have a better idea how to implement this gamma thing, and you have to be careful in terms of this, okay? So I think time's up. Let me stop here. So next class will, as I said, we'll take a deep look at this F statistic, because F statistic essentially is a key to the empirical testing, and we're looking at some deeper implication of this F statistic, and also look at the Charles test. Okay, so Charles test is probably a classical application of this F statistic, and it's widely used in empirical studies. So there will be next class. Okay.
Just one general question. Do researchers actually use this when they are formulating hypotheses, like for normal research work? Like, is it more like get to know, like when you're thinking about research idea and you get an idea, trying to put it in this form, is this something that people implement?
Yeah, of course, because you want to do, when you have some story, of course, after discussing model, then you need to figure out, because this is how to take the theory to testing, right? So you have the data, you have the model, you have theory. The next step, obviously, given theory, what's the restriction implied given the model? Then you basically test the restriction, testing the hypothesis. Hypothesis must be implied some restrictions. That's how you implement this, theoretical prediction with this empirical exercise, with statistical tools. That's really that's the case. Obviously, a lot of time you just test whether it's coefficient sticky or not.
Yeah.
That's pretty easy one, like whether we just equal 0. But even when you're testing this one, you also have some theory, basic theory that inflation will have impact. Or in this case, beta swing equals 0, your GDP will have impact on foreign investment decision. That's a theory. The non-hypothesis that no impact, but that's the restriction there. So that's probably more. But sometimes it may not be that straightforward. Sometimes you only impose this kind of restriction. Again, depending on how you specify the broader model and what the particular theory you want to tell. Okay. But that's pretty much that's kind of a general way of zeroing this empirical testing with if we have some theory for this. Okay. All right. So let me stop here and.